Yes, David? Okay, one last call. Anybody need a hard copy of the Thank you. All right, here we go. Here's where we left off as of last time, and you don't need to know the name of this, but you do need to know one big fact about this point in the process. Remember that as of this point right here, the glucose molecule has split in half, right? So there are going to be two of these per glucose molecule. You now have your body doing twice the number of reactions from this point on compared to the number it took to split the glucose up in half. All right, so look at what comes next here. You've got several different inputs in getting from this stage right here down to here. So notice you're adding a phosphate. You are now, and this is good news, you're going to reduce NAD plus. So you're going to make, in the process, make NADH. That is the dream of every step in catabolism. So this is good right here. This is good for making ATP. I'm going to have to keep this a little bit small in the right, so let me try to blow that up a little bit more even to compensate. I have to fit several things on this one page. So this is good for making ATP. That's everything that you would hope for. And this name right here, you don't need to know. So don't need to know the name, it's not that important. Now, this whole thing right here, which is the only detail I'm going to add, other than what's already here, is something about the way this looks thermodynamically. So delta G, how much does this want to go, is kind of the question. It's not large, positive, or negative, and that's kind of a theme for the reactions that aren't really hot control points. The rest of them, it's kind of in nature's interest to say, well, if we should ever need to run this process backward, let's make several places that it's not an issue if it runs backwards. That's kind of the logic here. Okay, and look at what you're looking at now as the product. This has two phosphates. And now we're to the point where we're talking. This is good for making ATP. So I'm not going to do anything other than color the phosphates at this point. There's a phosphorus and there's a phosphorus. And again, loaded up onto just 3 carbons. 2 out of the 3 carbons in that molecule are esterified to a phosphate. All right, so then here's our first good news on the ATP front as you look at the next one. This step right here, this next step, produces ATP, and it has, as a whole, a delta G that will tell you that this really does want to go. So it's both large and negative. Alright, so this one, I don't think that enzyme name is all that important either for this kind of class, so you don't need to know that one. And notice what has happened here for the first time. In this process, that's the first molecule of ATP that you got out of the whole thing. Now, keep in mind, all this has to be doubled. So for every glucose molecule that goes into the front end, you're now getting 2 ATP molecules out of it, even at this stage. Okay, it's starting to look like maybe this is going to be worthwhile. This right here, this next step, beginning with the compound that just has 1 phosphate, I'm going to say that this is just an isomerization. And so for that reason, delta G0 prime isn't large, positive, or negative. And this is an enzyme. Yeah, it's nice, but you don't need to know that. This gets us lined up with this final step, or next to the final step right here. And I hope what you're going to see is, I'm going to tag these carbons involved, those two spots right there. Those are the carbons. If this were your first semester of an organic class, I hope what you would do would be to look at this, what you start with, and what you end with, and you go, oh, this is a dehydration of an alcohol, and what would that word be? Just dehydration? There you go. That's one of the first reactions you get to in order to make the final product, to make an alkene. So I hope you're on familiar territory there. Enzymes, sure, that's cool, but you don't need to know that. Okay, again, this reaction right here is not a large delta G prime, either positive or negative. There should be a theme, I hope, that's starting to emerge for you, and we're going to make one more review pass. Most of the steps in glycolysis really aren't that demanding thermodynamically downhill. There's just a selected few of them, and wouldn't you know, those are the control points. Well, the rest of them are just kind of wishy-washy. And then you finally get down to the final step. You have this alkene going into it, and you do want to know this. Here's a step where it looks like there's some good news, and there is. This now again produces ATP. Delta G is large, and it's negative. It's very spontaneous, and I'm writing under part of the screen, sorry. Very spontaneous, wants to go. And as of the end, you have this compound right here that's got no phosphorus in it anymore. At the top of the page, near the top of the page, you were to the point where glucose's 3 carbons were loaded up to the tune of 2 out of 3 of them had a phosphate. Just 1, 2, 3 steps later, when it's all over, there are no phosphates in that compound. Both of them have been transferred, and in transferring they made 2 good news items. There's an ATP produced. Neither one of those phosphates gets wasted. Both of them productively make ATP. The name of the final compound is a name that you do need to know. Pyruvate. And let's just think about that and give it a few little descriptors, why it's important to know it. It is now a carboxylic acid. But it's more than that. It's also a ketone. If you want, it's the simplest, quote, beta keto acid. So here's carbon number 1. There's number 2, and there's number 3. You start with the most oxidized end. So the ketone is on number 2. There's 2 of your functional groups from organic coming back. Nature was doing this long before we knew what they were. The obvious thing, of course, is that it has 3 carbons. And please don't forget, there are 2 of these for glucose. And also remember that this is the end product of glycolysis. You start with glucose that has, well, if it's in its cyclic form, it has no carbonyl groups in it. No acid, no ketone, nothing like that. It's 6 carbons, 5 of them in a ring, 1 of them dangling off. And when you're down to glycolysis, its conclusion points you to, well, we have a carboxylic acid, we have a ketone, and we've got a methyl group out here. None of those functional groups were in your starting compound of glucose. It's a bunch of swapping reactions around. 2 phosphates have come and gone, and now you're down to this. This is also going to be gold in the next stage, which we'll get to. But for now, you're just looking at that one little molecule. Okay, so what I want to do is step through another couple of pages that are a level up, kind of a layer removed from the reactions. But we'll close the class by coming back to this page and the one that came before it and do kind of a high-level summary and review again. One more time through it with not so much detail that time. So we got to think about what happens and what the real point is. Now, I understand that as you learn these reactions, it's awfully easy to get to thinking that, oh, the point of the whole thing is to transform glucose from 6 carbons into 2 3-carbon pieces. That does happen, but that's not the goal. The real gold is what happens to the NADH that gets made in glycolysis. We'll step back through it one more time and kind of pinpoint that. So there are 2 branches of the world to think about. The first one is when oxygen is present, and that's what we'll say is normal. At least you hope that oxygen is normally present. You're breathing it, it's circulating thanks to the hemoglobin in your red blood cells, distributed out to the tissues all the time. You want to be fully oxygenated. Have any of you had these little finger clips put on your fingers that measures % oxygen? Okay. Do any of you don't have to tell us, 'cause I guess this would be medical information, but some people, it seems like, just habitually run a little bit lower than others on oxygenation. My numbers are always above 99%, and there's one family member of mine who appears to be totally healthy that's never above 98. I'm not sure what the difference is. Maybe they're not as healthy as they look, but they sure don't look like anything's wrong. But we're going to call that normal. So here's what matters in this circumstance. Now, NAD is actually one of the critical requirements for glycolysis to happen. Right? You need this stuff around in order to keep fuel from backing up and you running out of energy. Okay, now remember that NADH, the other part of this, is something which, good news, is actually made during glycolysis. However, it is then reconverted back to NAD+. Okay, this is good. This way, if there's oxygen present, it's kept in supply for when it's needed. All right, and if all conditions of your life and activity were conducted under these conditions, there would be no need for thinking about option 2. But the fact is, you do need to think about option 2 because sometimes there's not enough oxygen present. Now, that's not to say that you put yourself in a gas chamber that's filled with nothing but nitrogen. There can be oxygen absent, at least not enough of it present under conditions we would kind of think of as normal. So this would be anaerobic conditions. There are some organisms that function like that. That's not us. But for us, the more likely situation that makes this true is if you're looking at intense exercise. Do we have any athletes, bodybuilders here, anything? Okay. What do they tell you, Peyton, about going aerobic? Is there a plan for any athletes that you know of to deliberately try to push yourself into that metabolic zone part of the time?
Yeah, like when we do like full-out sprints, you're going to push yourself until you can't, and then you'll get like a good few minutes breaks to catch your breath.
Okay, so that's deliberate, right? They're training you to push to that point. Now, I think the point is not that going aerobic will make you better. I think it's that if you push that far, then you know that maybe there's not much benefit to pushing farther, and in pushing that far, you're starting to build your VTO max. I'm guessing that's what they're struggling for athletically.
Yeah.
Does that sound credible?
Yeah.
Okay. But in doing that, though, you do push yourself to that point, and in order to keep glycolysis running at all, so that you don't die, Peyton, from going through normal practice, here's what we've got to have. You've got to have NAD plus from, let's say, some other source. Because oxygen is not keeping up to regenerate this stuff fast enough. So here's the reaction that happens. It starts with pyruvate, and that is the compound that we just looked at the end of the glycolysis picture. I'm drawing it out now in a full condensed structural formula view. Okay, so there it is. Here's pyruvate. This is saying that the final product of glycolysis is able to kind of cycle back on itself and help you by doing this. You've got NADH, and there's always going to be a proton around somewhere. This is going to be available because of the fact that you are doing glycolysis. All right, so they sent you out, Peyton, and made you run until it hurt, and this is the stage you're at as of there. There's not enough oxygen to regenerate NADH, so what happens is pyruvate is now taking the place of oxygen. It's going to serve as the oxidizer. In the process, it's going to get reduced itself. Remember, in every oxidation, redox reaction, something gets oxidized and something else gets reduced. Okay? You wanted to get to NAD+, and you're certainly able to get there, but look what happens to your pyruvate. It's going to be reduced to an alcohol, and that should recall your organic class at some point, I hope. So this is now a molecule called lactate. And the other product, which you care about the most, is NAD+. That's why you do it. So say, this is why you want this to happen. Another way to think of it is that NADH is now available, even though you don't have any oxygen around to generate it. Okay, that's good. You can now keep living. That's the good news, right? So you don't die. And the anaerobic conditions are temporary. So here's how they get reversed. Let's say something like this. Your temporary conditions are reversed like this. Lactate gets oxidized, and we don't need to worry about the exact compound that does it. It gets oxidized back to pyruvate once the crisis is over, and then the pyruvate is going to continue as if nothing ever happened. Now that is not the part of the chapter we're in yet. We're not in catabolism of pyruvate. We're just stopping there because that's where glycolysis ends. Glycolysis can function aerobically, which is normal, or it can function anaerobically by a creative use of the last product in glycolysis. Turns out it's not just something to burn for energy farther on down the line. It can also help you by going back and assisting the cycle, should that be necessary. The symptom that you've gone anaerobic is, if you do it long enough, you'll start getting a burning sensation in the muscles that you work the hardest. And it's not too surprising, I guess, if you look at a molecule like that, you're going, carboxylic acid, that's the strongest acid known to organic chemists. And it's not as strong as sulfuric or anything, but that's nature's strongest acid. And if you start building that stuff up in muscular tissue, probably no surprise, it's going to start hurting. That can't possibly be comfortable. I'm told by hunters that if you shoot a deer after it has run a long time, the meat tends to taste sour, right? Because the deer has built up a lot of lactate. I'm not a hunter myself, so I don't know that by experience, but yeah, it's a real thing. Okay, so do they push you to the point of burning muscles?
Sometimes, yeah.
Yep. Okay, so you've done that reaction, and then you hope it goes away and gets reversed pretty soon.
Yes.
Okay, so then this last piece is the final part that you would have had in this chapter summary, and we'll use this to kind of bounce back to a review in a few minutes here. So here's the control of glycolysis. It's not always wide open as fast as it'll go all the time in every cell. There'd be no point in that. And I think the reason is pretty obvious. If you're exercising, you need more ATP because you're consuming it more and you need to regenerate it. All right, if you're asleep, you probably don't need as much ATP, unless you're like me and kind of kick around a lot. Okay, so there are three main control points, and all of them come at enzymes. And you'll need to know these. Hexokinase is one that you need to know by name. Phosphofructokinase, again, another one to know. And pyruvate kinase, know that one. These are not just randomly picked out of the list. These are the enzymes that have the say-so over how fast this reaction is going to run. So these are like your cops. And each one of these also is parked at a spot where you have a large and negative delta G. In other words, they're not easily reversible. Now, that doesn't say that it's impossible. It can happen. But these are not the wishy-washy reactions. Okay? These three are where there's something that happens where on the product side the bonds are so strong that to run the whole thing in reverse, not so easy, not impossible. So nature has handed us this sequence of 10 reactions or so with only 3 of them picked out as special compared to the rest. All right, the first one, hexokinase. And now we're going to start tying back to the part of the class where we talked about enzyme inhibitors. This stuff right here is the product of this step. It's the product of the first step. It now inhibits its own formation. It inhibits making, let me say it like this, making more of itself. Okay, there's a strategy to that, which is that the more of this you have, you've built up a signal. More of this means that there's probably enough, there's plenty of energy available. And that's a good logic to have built into a metabolic sequence. Think what it would be if it were the opposite. Let's say that glucose 6-phosphate comes off of the enzyme that just made it and goes, we actually need a whole lot more like me. I know you just finished up. That would be forcing the whole thing to accelerate early on in the process. And that's the other thing here. Look at where it's placed. Early in the process, there's a way for nature to say, we've got a lot of the product buildup, and it's only the first step. So let's not go spending a lot of time and reaction chemistry later down in the process if we know we don't need it. That's a checkpoint first thing in the line. And there's more like it. Again, this next step right here, phosphofructokinase, is stimulated by ADP and fructose 2,6-bisphosphate. Okay, that's a mouthful, I know. So let's kind of take that apart. This right here, ADP, is a signal. What ADP says is we need more energy. I actually saw that there's a company now that is proposing to sell you ADP in tablets that you chew up and swallow, which seems a little odd to me because, well, for the first thing, when it goes into your stomach, it hits low pH, and then you have to count on it going into your gut and getting absorbed and getting out to the right cells and so forth. But the logic, kind of the sales pitch for this whole thing was, well, if you want to really stimulate your metabolism, what you need to be doing is increasing your amount of ADP, right? Because that will, and that's true, it will speed up metabolism. On the other hand, there is another way to build up a lot of ADP without paying a dime or swallowing anything. And what is a good way to build up ADP? Exercise. It's free, right? And you don't have to swallow anything. But that's still the logic, right? The minute you build this up, let's say this. If you have lots of this, it says we need more energy. Okay, your cells are starting to feel the pinch and need to generate more ATP. Well, in that case, it's good to have a rate-limiting enzyme that's able to get the signal. Okay, knows it's time. For more energy. That's control point number 2. And then fructose 2,6-bisphosphate. Okay, let's think of what's happening if that's building up. If this builds up, it says that the glycolysis process itself is slowing down. Now, that's not all bad. There needs to be ways to speed it up and to slow down the whole process. Okay, but this, what the two of these do together is it makes glycolysis sensitive to the energy needs of the cell. All right, so that's a good logic to have built in. Okay, the last one, the last control point, pyruvate kinase. Know these enzyme names, where they are, and their logic. This one is inhibited by one thing and stimulated by another. Okay, now what you want to remember here is that this is This is the very last in the sequence. And that means that because it's the last, it's a choke point. If you slow things down in the last step, you slow up the entire chain. Okay, that's a fact, and now nature goes, okay, now that that fact exists, what do I do logically to exploit it? And it does. So if there's a lot of ATP, there's a logic here which says that lots of ATP means we don't need this sequence to be running flat out. So this means that the cell has plenty of energy in the form of ATP, and there's no need to operate glycolysis fast. Okay, it's stimulated though. This last step is stimulated by fructose 2,6-bisphosphate. So let's trace that to where it sits in the process. It's early. This thing comes early in the process. If there's lots of it, then we'd better start thinking about using it. Okay, lots of it means don't slow down. I'm running off the screen there. Don't slow down the final step. So in other words, this is a way of coordinating the front end and the back end. So it coordinates an early step and a late step. Now the first two control points were kind of logic checks one at a time. The cell senses what it needs and what it needs to do. This last one right here is kind of like you know those 3-digit numbers on your credit card, if you have to give a credit card? Those 3 are a check that the retailer is able to do just to make sure that the first numbers were entered right. This is a logic check on the earlier part of the process. I don't know if that helps or not, but yeah, so that's the process. And we're going to call that the end of glycolysis, the new stuff. But what I want to do now is a quick pass through the reactions again. Who wants to use hard copy for this stage? You want one here? Okay, I'm just going to take. Okay. I'm just going to take the same pages and go through them again, but this time with less detail. Okay, I'm going to try to point out the things that lend themselves to questions that tend to get missed a lot. I don't know if that's the chemical approach or not. But here's a less detailed pass through the whole thing, looking at things that may have kind of gotten mixed into the details a lot. So let's try to make a few things stand out. This first step right here consumes ATP. That doesn't sound like it's good at all. Here's another step that looks like it consumes ATP. And that doesn't sound good either. If you look though onto the next step of reactions, here is some good news. This produces NADH, and that is going to be a hero later when it comes to making ATP. The next step makes ATP, as does the very last step. And then here's one big thing that you don't want to lose on this second page at all. Everything compared to the number of glucose molecules happens twice. Right, so you're starting to get payoff now. You had to invest 2 ATPs to begin with, and you're getting a total of 4 out of it. So that's an overall yield of 2. That's sure not much ATP compared to what's made by other processes, but that's a step in the right direction. So here are your 3 payoffs, right? NADH here, and ATP in 2 later steps, after investing ATP at 2 steps on the front end. And let's put one other layer on this, and that is the control points. The very first step is a control point. And then not long after that, here's another control point. The first one, of course, you can kind of understand why that one needs to be, somebody keeping an eye on that. The very last one is a control point. Okay, I'm going to leave that as no more detail other than that, unless you have questions, like you wanted to see, well, which steps do fill in the blank. But I think it helps to see one less detailed version of the whole thing. Okay, any questions on that? Otherwise, we'll call it done for the day. Reactions are too intense to do for a whole day, right? That tends to not work well. Imagine doing this for 3-4 weeks on end, and then one exam to cap all that off. I don't think so. Okay, sounds good. See you next time. Have a good day.